Hello, my beloved viewers. I really hope that you are doing well. Welcome to our today's class. It's our fourth lesson on the topic Hooke's Law. So as usual, let me commence by giving you the quote of the day, which states that pressure can burst pipes, but it can also make diamonds. So we'll discuss that quote at the end of our class today. So today we are looking at the parallel and series arrangement of springs. So let me start with the parallel arrangement of springs. So whenever springs are arranged in parallel form, remember they appear like parallel lines. Remember, parallel lines will never intersect each other. So when springs are arranged in this manner, that is in like parallel lines, then we say that the springs are arranged in parallel form or in a parallel manner. So this is the parallel arrangement of springs. So this spring is having a spring constant of 2. This one has a spring constant of 7. Then the other one has a spring constant of 3. Then, of course, they are supporting a weight of W newtons. So whenever springs are arranged in parallel, if you want to find the spring constant or the total spring constant, sometimes we also call it the effective spring constant, you will take the sum of the spring constants of individual springs in the parallel arrangement. Like in this case, if you want to find the spring constant, the total spring constant for n number of springs, then the K total, that is the total spring constant, will be equal to the spring constant of the first spring plus the spring constant of the second spring plus whichever number of springs that you are using up to n, the spring constant of the nth, which is the last spring. So that means if you are dealing with maybe 3 springs, then the spring constant will be equal to the spring constant for the first spring plus the spring constant for the second spring plus the spring constant for the third spring. Maybe if you are dealing with maybe 5 springs, then we'll talk of K total being equal to K1 plus K2 plus K3 plus K4 plus K5. So up to Kn simply means that you are dealing with infinite number of springs. So we are saying that whenever springs are arranged in parallel, if you want to find the total spring constant, you will just take the summation of the individual spring constants of those springs which are arranged in parallel. So we can look at an example. So assuming this first spring has a spring constant of 2, the second spring has a spring constant of 7, then the third spring has a spring constant of 3, that is a Newton per meter. Then we'll talk of K total being equal to the spring constant for the first spring, which is K1, plus the spring constant for the second spring plus the spring constant for the third spring. So that K total will be equal to the summation of 2 and 7 and 3. So you take 2 plus 7 plus 3, then you will obtain 12 Newton per meter. Now, whenever springs are arranged in series form, remember the series form is now the opposite of parallel forms. So whenever springs are arranged in this manner, that is in this vertical manner, such that one spring is attached to the other spring is also attached to the other, then this arrangement of the spring, this is what we call the series arrangement of spring, the series arrangement of spring. Then whenever you want to find the effective or the total spring constant for springs which are arranged in series, you will take the reciprocal. The reciprocal of the total spring constant should be equal to the reciprocal of the spring constants of the individual springs which are arranged in series manner. So for example, if we are dealing with n number of springs, then 1 over total spring constant should be equal to the reciprocal of the spring constant of the first spring plus the reciprocal of the spring constant of the second spring up to the reciprocal of the spring constant of the nth spring. So if we want to find the spring constant, which is the total spring constant, that is 1 over K total, will be equal to 1 over K1. Remember, K1 represents the spring constant for the first spring, and plus 1 over K2, which represents the spring constant for the second spring, and so on and so forth until we get to the nth number, the nth spring constant. So we can look at an example here. So that means if you want to find the spring constant maybe for 3 springs, So that means 1 over k total will be equal to 1 over k1 plus 1 over k2 plus 1 over k3. If you want to find the total spring constant for maybe 5 springs, 1 over k total will be equal to 1 over k1 plus 1 over k2 plus 1 over k3 plus 1 over k4 plus 1 over k5. So we can look at an example here. So assuming my first spring here has a spring constant of 2, the second spring having a spring constant of 7, and the third spring having a spring constant of 3 Newton per meter, of course supporting a weight W Newton, then 1 over k total will be equal to 1 over k1. That is 1 over the spring constant for the first spring, which is actually 2. So 1 over k total will be equal to 1 over 2 plus 1 over the spring constant for the second spring. The second spring is 7 Newton per meter. So that means we'll take its reciprocal. So that is 1 over 7 plus the reciprocal of the spring constant of the third spring, which is 1 over 3. So you take the summation. Actually 1 over 2 plus 1 over 7 plus 1 over 3, you'll obtain 41 over 42. So that means the reciprocal of the total spring constant is equals to 41 over 42. So that if you want to find the value of kt, which is the total spring constant, we'll either take the reciprocal or you simply cross multiply. So if I take the reciprocal on both sides of this equation, so that means kt over 1 will be equal to 42 over 41. But kt over 1 is just kt. So kt is representing the total spring constant, so which is equals to 42 over 41. So you divide this, you will approximately find 1.0244 Newton per meter. So remember, we are using exactly springs, identical springs, or springs of the same. If you compare, this is 2, this is 2, this is 7, this is 7, this is 3, this is 3. So we are using springs which have identical or the same spring constant. That is for the parallel case and for the series case. So if we compare the total spring constant for the 3 springs arranged in parallel, we got 12 Newton per meter. If we use the same springs but arranged in series, we are finding the spring constant to be 1.0244. So you compare this value, that is the k total in series and the k total in parallel, you realize that the k total in parallel is larger than the k total in series. So that simply tells us that if identical springs are arranged in parallel and in series, the springs which are arranged in parallel, they will always give a greater or a larger total spring constant than the same springs which are arranged in series. So we can easily conclude that whenever springs are arranged in parallel, whenever identical springs are arranged in parallel, they will always give a larger value of the total spring constant as compared to the value for the total spring constant when springs are arranged in series. So if you want to increase the value of the total spring constant given a number of springs, you simply arrange them in parallel. But if you want to reduce the total spring constant of a given number of springs, then the easier way is just to arrange such springs in series. So maybe somebody can ask you that maybe 3 springs. He had 3 springs. Explain how he could obtain the largest possible value of the total spring constant. So the answer will be by arranging the springs in parallel. Somebody can also ask you that how can you reduce the effective or the total spring constant of springs? So the answer will be by arranging such springs in series. So later on, when we'll be looking at electrostatics 2 in form 3 work, we will realize that the way of finding the total or the effective spring constant is similar to the way of finding the effective or the total capacitance of capacitors. So the way capacitors behave when arranged in parallel is the same way that springs also behave. Then also the same way that capacitors behave in series is the same way that springs will also behave in series. So later on, that is in electrostatics 2, we'll see that also to find the total capacitance or the effective capacitance of capacitors arranged in parallel will simply be taking the summation of the capacitors of the individual capacitors. But if you want them in series, then we'll be taking the reciprocal of the individual capacitors. So next we look at an example, that is of how to find the effective or the total spring constant of springs arranged in parallel and in series. So the question reads that the spiral springs shown are identical. Remember, whenever springs are identical, it means their spring constant is exactly the same. That is, the spring constant for individual springs are exactly the same, such that maybe if one spring has a spring constant of 2 Newton per meter, then the other springs will also have spring constants of 2 Newton per meter. Remember, when springs are identical, it means they are the same or they have equal value of the spring constant. Now, given that each spring has a spring constant of K is equals to 300 Newton per meter, determine the total extension caused by 90 Newton weight. Then we are told to ignore the weight of the spring and the connecting rod. So to ignore simply means we will neglect, or we will assume that this connecting rod and these springs, they have zero weight or they have no weight. So that is what it means to ignore the weight of the spring, such that in our calculations we'll only consider the weight or the extension of the spring being caused by the 90 Newton weight or force, but not the weight due to the springs or the connecting rods. So because they want us to determine the total extension, and we know from Hooke's law that force is equals to Ke, therefore to find the total extension, we'll need to find the K, and we also need to find the weight, that is W. But from the question we are given the weight, which is 90 Newton. So our task is to first find the spring constant. So there are two approaches. Let me start with the first one. So consider these springs. So I've labeled these springs: spring 1, spring 2, spring 3, spring 4, and spring 5. So our first task is to find the effective or the total spring constant for the arrangement of the springs 1, 2, and 3. If you observe springs 1, 2, and 3, they are actually parallel to each other. So if you want to find the effective or the total spring constants, the total spring constant for the first 3 springs which are arranged in parallel to each other, we'll simply take the summation of the individual springs. So because there are 3, therefore we'll find that K, that is the total spring constant for spring 1, 2, and 3 combined, will be equal to the summation of the individual spring constants of the 3 springs, which is K1 plus K2 plus K3. That is because they are arranged in parallel. So because we are told that each spring has a spring constant of 300 Newton per meter, and that the springs are identical, therefore it means that to find the K total for spring 1, 2, and 3 combined, we'll simply take 300 plus 300 plus 300, which actually gives us 900 Newton per meter. Then we'll also need to find the total or the effective spring constant. That is so that means we have already combined the K1, K2, and K3 into 1, such that we have found it as 900 Newton per meter, the 900 Newton per meter. So if we want to find the spring constant, remember spring 4 and 5, they are also parallel to each other. 4 and 5 are also parallel to each other. So if we want to find the effective or the total spring constant for the springs 4 and 5, we'll also take the summation of their individual spring constants. But you are told that the springs are identical and each has a spring constant of 300 Newton. Therefore, the total spring constant for K4 and K5 will be equal to K4 plus K5, which is equals to 300 plus 300, which gives us 600 Newton per meter. Sorry, this should be per meter. Newton per meter, or Newton meter power -1, because they are also arranged in parallel. Then to find, now remember we have combined 1, 2, and 3. So 1, 2, and 3 together, that is combined, we got their spring constant as 900. So we can represent it with just one spring, which is 900 Newton per meter. Then we have also combined spring 4 and 5. So K for 4 and 5, we found it as 600 Newton per meter. So that means if we combine it into 1, it becomes the 600 Newton per meter. So if we assume that these three, they are combined into one spring, and also these two are also combined into one spring, then we are obtaining two springs, that is of 900 Newton and 600 Newton, which are actually in series to each other. So to find the total or the effective spring constant for the springs which are arranged in series, we take the reciprocal of the individual spring constants. Therefore, to find the K total, that is now for these two springs, remember I've obtained this diagram as a result of combining these three to make it one, that is the 900, that is the K1, 2 and 3 gave us 900 Newton per meter. But K4 and 5 gave us 600 Newton per meter. So to obtain, so that means that if I take these 1 and 2, then I arrange them in that manner, so they will actually be in series with each other. They will be in series with each other. So remember, to find the K for springs in series, we usually take 1 over K total is equals to the summation of the reciprocal of the spring constant of the individual springs. So if I want the K total now for the whole system, I will take 1 over K1, 2, 3, which was 900, plus 1 over K4 and 5, because they are now in series with each other. So if I want 1 over K total will be equal to 1 over K1, 2, 3. K1, 2, 3 was 900, so 1 over 900 plus 1 over K4 and 5. K4 and 5 was 600 Newton per meter. So I'll obtain 1 over 600. So I take 1 over K total will be equal to, you take 1 over 900 plus 1 over 600, you'll obtain 1 over 360. So if I take reciprocals on both sides, I'll find K total being equal to K over 1 is equals to 300 over 1. But K over 1 is just, K total over 1 is just the same as K total. 360 over 1 is just the same as 360. Alternatively, you can also cross multiply such that you'll have 360 times 1, which is 360, being equal to K total times 1, which is equals to K total. Therefore, K total is equals to 360 Newton per meter. So after having found the K total, we know that the F total, that is from Hooke's law, F total should be equal to K total plus E total. That is the total force or the total weight acting on the spring must be equal to the product of the total spring constant and the total extension. Then we are told that the total weight acting on the system is actually 900 Newton. So the total weight is 900 Newton. So that means that the it is 90 Newton. So that means 90 Newton will be equal to K total. K total, we have found it as 360 Newton per meter times E total, that is the total extension. So 90 is equals to 360 times E total. So to find E total, I'll divide both sides by 360. So I take 90 divided by 360, that is E total is equals to 90 divided by 360. I'll obtain 0.25 meter. So that is my total extension. We can also use another approach, that is the individual approach. So we talk of force, that is the force due to spring 1, 2 and 3 is equals to the spring constant due to spring 1, 2 and 3 and the extension due to spring 1, 2 and 3. So we find them individually, then that is we find the extension for this system, that is for springs 1, 2 and 3, then we will add it to the extension for springs 4 and 5. So of course we expect the answers to be exactly the same. So for us to find the extension for springs 1, 2 and 3 from Hooke's law, we need to have the the total weight or the force acting on springs 1, 2 and 3 and the total extension due to springs 1, 2 and 3. Now we know that springs 1, 2 and 3, because the weight is acting downwards, therefore the weight acting on springs 1, 2 and 3 is still the 90 Newton. Because remember, we did say that we are ignoring the weight of the springs and the connecting rods. But if we were assuming the springs had some weight, or if we were not ignoring the weight of the springs and the rods, therefore the weight acting on springs 1, 2 and 3 will be the 90 plus the weight of springs 4 and 5 and the ropes, this rope here and these other ropes here. But because we are told to neglect or ignore the weight of the springs and that of the connecting wires, therefore it means that the total weight acting on springs 1, 2 and 3 will be equal to the 90 Newton, which is acting from downwards. Then the spring constant for springs 1, 2 and 3, we had already calculated it. K1, 2, 3 was actually 900 Newton per meter. So there is no need of repeating ourselves. So if we just substitute values in this equation, that is force for acting on springs 1, 2 and 3 is equals to spring constant for springs 1, 2 and 3 times the extension for springs 1, 2 and 3, then we'll obtain 90 Newton being equal to K1, 2, 3 is 900 Newton per meter is equals to extension for springs 1, 2 and 3. So if I divide both sides by 900, therefore I'll obtain the total extension for springs 1, 2 and 3 being equal to 90 divided by 900, which is equals to 0.1 meter, the 0.1 meter. Then, so I've already found the extension due to springs 1, 2 and 3. So my next task is to find the extension for springs 4 and 5. Now from Hooke's law, we know that force is equals to Ke. Therefore, the force acting on springs 4 and 5 must be equal to the product of the spring constant due to springs 4 and 5 and the extension due to springs 4 and 5. Now we know that the force acting on springs 4 and 5 is still the 90 Newton, because also remember that we are ignoring the weight due to the springs and the rods. So the total weight acting on springs 4 and 5 is 90 Newton. Then the spring constant due to 4 and 5, we had already obtained it somewhere. It is here. It was 600 Newton per meter. So that means 90 is equals to 600 times E. That is extension due to springs 4 and 5. So if I make E 4 and 5 to be the subject of the formula, I'll divide both sides by 600. Therefore, I have E 4 and 5 being equal to 90 divided by 600. On simplification, you will obtain 0.15 meter. So that is the extension due to 4 and 5. I also have the extension due to 1, 2 and 3. So if I take the summation of the extension due to springs 1, 2 and 3 and also the summation of springs extension due to springs 4 and 5, if I add these two, I should actually obtain the total extension. Therefore, the E total will be the total extension due to springs 1, 2 and 3 and the total extension due to springs 4 and 5. So E1, 2, 3, I've already obtained it as 0.1. Then E4 and 5, I've obtained it as 0.15. So if I sum the two, I'll have 0.1 meter plus 0.15 meter, which gives me 0.25 meter. So you can either use this way or this other way, but please don't use both. In an exam situation, you just use one. You don't use both. Next, we look at our example 2, which reads that springs below are identical and have negligible weight. The extension produced on the system of the spring is 20 centimeter. We are required to determine the constant of each spring. So remember, we are already told that the springs are identical. So that gives us a clue or a hint that the spring constant for each of the springs is exactly the same. So if each spring maybe has a spring constant of 4, then each spring must have a spring constant of 4. So first of all, we identify what we have been given. So we are given the extension produced on the system is 20 centimeters. So this is the total extension. Then we are required to determine the constant of each spring. Then we are also given the weights. The weight acting on spring 1 and 2 is 20 and 20. Then the weight acting on spring 3 is only the 20 Newton. So if we want to find the K, we must have F and E. We must have F and E. We are given F. Then we are also given the total E, but not E for the individual springs. So for us to obtain E for the individual springs, we will need to find the summation. We'll first have to find the K. Then of course for F we are given. So let the spring constant for each of the springs be K. That is K Newton per meter or Newton per centimeter, whichever the case. So because the spring constant is the unknown, we give it a letter. So we are saying let the spring constant for each of the spring be K. Therefore, to find the spring constant acting on springs 1 and 2, it will be equal to, because remember 1 and 2, they are parallel to each other, so their effective or total spring constant will be the summation of the individual spring constants. So because we are saying that each spring has a spring constant of K, to find the K for springs 1 and 2, we'll take K1 and K2. But remember that we are saying that the spring constant for each spring is K. Therefore, the K1 is K and also the K2 is K. Therefore, the spring constant due to springs 1 and 2 will be equal to K plus K, which is equals to 2K, which is equals to 2K. Then, to find the force, because we already have the K, we can easily find the equation for the spring, the extension. We can easily find the equation for the extension. So, because we are given the total extension, we'll find the two equations for extension due to 1 and 2 and also extension due to 3. Then if we sum or if we add the extension due to the combined 1 and 2 and 3, it should be equivalent to the total extension. So our task here is to find the two equations representing the extension, then we equate it. We equate those two values to the summation of those two values to 20 centimeter or 0.2 meter, which are the SI units for length. So the force due to springs 1 and 2, or the force exerted or acting on spring 1 and 2. Now observe here keenly, spring 1 and 2, they are experiencing the weight, or the extension of springs 1 and 2 is due to the 20 Newton force or weight and the 20 Newton weight or the force. So the weight acting on springs 1 and 2 is 20 plus 20. Also, if maybe springs 3 had some weight, then the total weight that will cause extension for springs 1 and 2 will be 20 plus the weight of spring 3 plus 20. But the weight acting on spring 3, or the weight causing an extension in spring 3, is only the 20 Newton weight or force. Remember, the weight will always act downwards or towards the surface of the earth, or because of the gravity. So the weight cannot act upward. So you cannot say that for spring 3, the weight acting on it is this 20 plus the other 20. No. The weight only acts downwards. But because this weight and this other weight are already on the lower part of springs 1 and 2, then it means the extension due to springs 1 and 2 will be brought about by the forces 20 Newton and the 20 Newton, which is actually the 40 Newton. So the force acting on springs 1 and 2, or causing extension in spring 1 and 2, should be equal to the spring constant due to spring 1 and 2 and the extension due to spring 1 and 2. That is according to Hooke's law. So the force due to spring 1 and 2, we are saying it will be 20 Newton plus 20 Newton, because the 20 and 20 are below. They are below springs 1 and 2. Therefore, it means they are causing springs 1 and 2 to stretch or to extend. Therefore, the total force acting or causing extension in 1 and 2 will be the 20 Newton plus the 20 Newton, which gives us the 40 Newton. Therefore, 40 Newton will be equal to spring constant due to spring 1 and 2. Remember, spring 1 and 2, we have obtained the spring constant as 2K, because we assumed that the spring constant for each spring, we let it to be represented by K. Therefore, 40 Newton is equals to 2K times the extension due to springs 1 and 2. Therefore, if I make the extension due to springs 1 and 2 to be the subject of the formula, that means I'll divide both sides by 2K. So you get 40 over 2K being equal to 2K divided by 2K times E1 and 2. But 2K divided by 2K, they will cancel out, so that you remain with E1, 2. Therefore, the extension due to spring 1 and 2 will be equal to 40 divided by 2K. So if you divide 40 and 2, you'll obtain 20. So 20 divided by K, you'll obtain 20 over K. So we name this as our equation 1. That is the extension due to 1 and 2. I also want to obtain the extension due to 3, so that when I add the extension of 3 and the one due to 1 and 2, it should be equivalent to the total extension, or the extension of the system, the extension produced on the system. So from Hooke's law, we know that force is equals to Ke. So the force due to acting on spring 3 is only the 20 Newton. Remember, the reason we say this because weight acts downwards. Huh? Remember, weight depends on gravity, and gravity acts downwards. So this force will not cause the spring to extend. That is the spring 3 to extend, because it is on the upper side of spring 3. But the only force that is on the lower side of spring 3 is the one that will cause that spring to extend, because the weight acts downwards. The weight acts downwards and not upwards due to the gravity of the earth. So the force causing spring 3 to extend is only the 20 Newton. Therefore, F3 must be equal to K3 times extension due to spring 3. Therefore, force due to 3 is 20 Newton. Remember, we have said that it is 20 Newton because this is the only one causing this spring 3 to stretch. But for spring 1 and 2, both 20 and 20 are below springs 1 and 2. So because the weight acts downwards, therefore the summation of the 20 and the 20 will cause spring 1 and 2 to stretch. That's why for this case we are using 40. That is the 20 plus the 20. But for this case, it is only one force that is below it, which means this spring 3 is extending due to only the 20 Newton force, and therefore the force causing the extension is 20. The spring constant, we said that let the spring constant for each spring be K. Therefore the K3, or the spring constant due to 3, will also be K, multiplied by the extension due to spring 3. So if I make E3 to be the subject of my formula, that means I'll divide both sides by K, also this other side by K. So K divided by K, they will cancel out, so that we remain with K over 20. Therefore E3 will be equal to 20 over K, which is I'm naming this to be my equation Roman 3, or my equation Roman 2. But we are given from the question that the extension produced on the system of the spring is 20 centimeter. So extension is 20 centimeter, but we know the SI unit for any length, whether extension or distance, it must be in meters. So extension in meters, so remember 100 centimeter is equals to 1 meter. So to obtain it in meter, we'll take 20 centimeter divided by 100 times 1 meter, which gives us 0.2 meter. So we are just ensuring that the units are uniform. So we know that the total extension due to this system will be the extension due to spring 1 and 2 and the extension due to spring 3. That is, the total extension will be the extension of one of the springs here, that is 1 and 2, plus the extension due to spring 3. The extension due to spring 3. So the extension for 1 and 2 will just be equal to the extension of one of the springs. So the extension due to springs 1 and 2 plus the extension due to spring 3 should give us the total extension. So that's why we are saying that E total, that is the total extension, is equals to E1 and 2, that is the extension due to spring 1 and 2, plus E3, that is the extension due to spring 3. So E total is equals to E1, 2 plus E3. But E total, we are given the total extension as 20 centimeter, which you have obtained as 0.2 meter. So we'll say 0.2 meter is equals to extension due to spring 1 and 2. Remember from our equation 1, the extension due to spring 1 and 2 was 20 over K. So we'll substitute it here, 20 over K plus E3. From our equation 2, the extension due to spring 3 was 20 over K, where K is the spring constant for each of the springs. So 20 over K. So that means I can decide to multiply each and every term by the LCM. The LCM for this case is K. So that this one times K, the K and K will cancel. I remain with 20. 20K over K. K and K will cancel. I remain with 20. Then 0.2 times K. I remain with 0.2K. Therefore, 0.2K is equals to 20 plus 20, which is 40. So 0.2K is equals to 40. If I divide both sides by 0.2, I'll obtain 0.2 over K. The K and K, the 0.2 and 0.2 will cancel, so that I remain with K. Then 40 divided by 0.2, I'll obtain 40 over 0.2. Therefore, K, you simplify this, you'll obtain 200 Newton per meter. So those are the SI unit for spring constant. Remember, in some cases you can also express it in a centimeter. So if you want to express it in a centimeter, so the K will be equal to 200 Newton divided by, remember, Newton per meter means 200 Newton divided by 1 meter. So that means 200 Newton divided by 1 meter. So I'm converting the 1 meter into centimeter. So remember, 100 centimeter is equals to 1 meter. What about 1 meter? So it will be 1 meter over 1 meter times 100 centimeter. So you take 200 Newton divided by 100 centimeter, you will obtain 2 Newton per centimeter. But as we said, it is always good to leave the answer in the SI unit. So for this case, 200 Newton per meter is the correct answer. Unless the question wants you to leave the answer maybe Newton per centimeter, then you can also give it as 2 Newton per centimeter. But for if you want to be safe, always ensure that you leave answers in physics in their SI units, which is the Newton per meter. Alternatively, somebody can also approach the same question in a different manner, such that you just say force, that is from the Hooke's law, force is equals to KE. Therefore, F total must be equal to K total times E total. So the F total acting on the whole system is 20 Newton plus 20 Newton, which is 40 Newton. Then the total extension, that is the extension acting on the whole system, that is the extension produced on the system, is 20 centimeter. That is, E total is equals to 20 centimeter. So to convert it into meter, we divide by 100 so that we obtain 0.2 meter. Then from Hooke's law, we know that force is equals to KE. So force, that is the total force acting on the system, which is 20 plus 20, which is 40 Newton, must be equal to the K total times the E total, that is the total extension. The total force acting on the system is 40 Newton. The total extension acting on the system is 0.2 Newton. So if 40 is equals to K total, that is the spring constant for the whole system, times 0.2, I divide both sides by 0.2, I will obtain K total being equal to 40 divided by 0.2. So 40 divided by 0.2, you will obtain 200 Newton per meter. Or you can use the same method here to convert into Newton per centimeter, which you will obtain 2 Newton per centimeter. But as I said earlier, it is always good to leave the answers in the SI unit, that is in physics. So my final answer is 200 Newton per meter. Then I have an exercise here which I recommend that students should try to test their grasping of the concept that we have learned earlier. So question 1 reads that determine the total extension produced in the arrangement below, given that each spring has a spring constant of 50 Newton per meter. So the expected answer is 0.2 meter. So this diagram is actually for question 1. Question 2 reads that an object of weight 20 Newton attached at the end of a spring causes the extension of 0.5 centimeter on the spring. A, determine the spring constant of the spring in its SI unit. So the expected answer is 4000 Newton per meter. Part B, determine the weight of an object that will cause an extension of 0.86 centimeter when attached at the end of the same spring. So I've worked out, and the expected answer is 34.4 Newton. Then lastly, a light spring, spiral spring, extends by 4 mm when loaded with a load W. The spring is connected in series with an identical spring, full stop. The combination is loaded with a weight W. You are required to determine the extension of the combination in the SI unit. So I've worked out, and the expected answer is 0.08 meter. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that pressure can burst pipes, but it can also make diamonds. So the word pressure in this scenario, or in this case, represents our challenges in life. Therefore, the quote is encouraging us to see challenges as opportunities to grow and become better human beings, instead of believing that challenges come to destroy us. Yeah, challenges do not come to destroy us. Instead, they come to strengthen us. So just in the same way, good diamonds need pressure for them to be formed, human beings too need challenges for them to grow. And recall that we don't grow when things are easy. Instead, our mental strength only grows after we've overcome a challenging situation. And therefore, if you want to grow your mental strength, look for more challenges and look for solutions. And lastly, once it becomes clear that the target cannot be achieved, do not lower the target. Instead, increase your effort to match the level of your target. Thank you very much. For those who have not subscribed, kindly do me an act of kindness and hit that subscription button, and also turn on the notification bell so that whenever you upload a new video, you will be the first person to get a notification. Also, if you enjoyed the video, feel free also to like and also drop a comment. I would like to know what you think about these videos. Thank you very much. Actually, do me a favor, for those who have not subscribed, kindly hit that subscription button so that to help this channel to grow, so that to access even more students to benefit from it. Thank you very much. Until next time.